Hi guys. Hope you've been staying away from sharp objects because those hurt. Yeah. Normally this is drunk physics. Right now I'm drinking water, so I'm getting drunk off of water instead. I don't know why I can't get this thing to stay still. Bear with me here for a second. Okay, well we're just looking at a slideshow basically that I was doing for a thing I did in college. And I just kind of blew it with that one because I got way too in depth with it. But the thing is, I thought it could become something like a, I don't know, like a 30-minute lecture, a small, short course on how do we solve black holes? What are black holes? And the answer is actually not that simple. As you might imagine, it uses deep, deep mathematics, but I'm going to show you a small survey of some of that mathematics. Actually, I'm kind of actively here on Facebook. I got it in the other screen, and they're talking about this same question. So I thought I'd post it here. And I generally post these in a certain forum on Facebook. It's called Astronomy and Cosmology Discussion Forum, I want to say. It's over here in this, but just had some lunch, and I'm thinking about these black holes and stuff, and kind of got a lot bouncing around in my head, and I'm trying to put out some content, but I don't feel like making it drunk physics right now because I kind of went on a little bender for drunk physics, and I really was getting pretty smashed, and that's not a way I really want to live my life, like 5 days in a row. So took a little siesta, slept it off, drank some more water, you know, drinking heavily. You go, oh my god, let's make a series called Drunk Physics, and then everybody's like, come on, yeah, keep drinking and then do more drunk physics. It's not as fun as you think. But some of them, well, when I do drink, you can be promised some physics. So it's just going to kind of come out on a semi-regular basis when I feel like it. Give me a second here. I'm going to take a look at this thing and see which one to do. Okay, so I called this thing A Farewell to Time, The Voyage, and I put Rush behind it. And I got a C on this project because it was kind of poorly cobbled together when I was, I'll let you imagine what kind of metal. Yeah, it plays really lightly in the background like there. You really exactly trying to talk and hear that. Why did you do that? I'm like, I don't know. What is it actually saying in the background here? It's actually talking about a black hole. Like this phone. So, I mean, it was the cheesiest, like, nerdiest speech ever done. But this is what we're talked about. We're going to look into what makes black holes happen. Physics. How does it do what it does? What happens when it does it? Things about that. How do we talk about it? Well, we talk about it with mathematics. We use mathematics to talk about things that do things mathily. Okay? And then philosophy. What does it do? Of course, I didn't want to switch to that slide. This thing is not behaving very well because it was set up to be like a 7-minute thing, and it keeps wanting to do what it does and like in the background. So bear with me here. I'm going to try to work with this. You know what? Actually, let's go on. Let's go to the next slide. Do not play. So then I put a quote from Alice in Wonderland. Alice was beginning to get very tired of sitting by her sister on the bank and of having nothing to do. Once or twice she had peeped into the book her sister was reading, but it had no pictures or conversations in it. And what is the use of a book, thought Alice, without pictures or conversation? Oh wow, look how that worked. That's kind of how I did it in the class. And then I went on a rant about this. Let's see, I put a bunch of equations in here, and I want to explain what all these equations are before this thing goes like this. And seriously, I don't know how to get it to stop doing that, but I don't want it to actually move, so hold on. Okay, better. Now we have it in the editor here where you actually do it. You actually make the PowerPoint. It's not going to do anything now. It shouldn't anyway. I'm going to move this out of the way. So what are we looking at here? Well, we can actually kind of mouse over things and select them. This is the equation we're talking about right here. This is the Schwarzchild equation. ds squared equals 1 minus 2m over r dt squared plus 1 over that same thing there, dt squared, plus your standard equations for a sphere. I think there's something going on there. I'm not sure exactly how that works. All right, now that means nothing to anybody who's not a physicist or hasn't taken like physics enough to even like look at that equation and tell you what that says. But what this is it actually gives you a formula for being able to talk about distances in that space-time. So you think about a grid, okay? You got a grid with a bunch of squares on it. You got a square here, a square there. So as the universe expands, that square gets larger, but the things on the points stay the same size. We treat them like point particles. That's kind of how we talk about it. But in black holes, they kind of like to bend, especially when they get to a certain point right here. Now notice something that's going to happen to this equation if r equals 0. All of a sudden you're dividing by 0, and that is not okay in physics. You cannot do that. That means nothing. It doesn't mean anything. There has to be limitations on how small or infinitely packed things can be. But treating it like a point particle gives you a way to think about it simply. But this is just an estimate. It's like it tells you how things behave until it gets to a certain point. After that, we're just like, I don't know, it hits a wall of like sphere, like, and then just dissolves on that wall, writes itself on it, and codes it into like a three-dimensional CD, really, kind of. It's like a CD burner, like cosmic CD burners, but the CDs are three-dimensional. You can think of it like that. That's what some people think. That's what some physicists think. That's like Stephen Hawking and Leonard Susskind. Those would be the guys who want to talk about it like that. Other people just think it goes into another universe. I mean, who knows? Black holes might lead out to a white hole, so it kind of trumpets in, hits a singularity almost, but not quite, and then flings off into another. Where does it go? What happens? Who knows? See, look, that's what we're talking about when we talk about the philosophy. That doesn't matter. Nobody's talking about philosophy here. Well, we'll speculate on what kind of philosophy it could have, what it could mean, but I'm not saying what it does mean, because they don't know. And they told me they don't know, and I believe they don't know when they say they don't know, and if they don't know, I sure as hell don't. So it goes like this. But Riemannian spherical geometry has this property where if you go directly over the sphere, it just extends off into space forever. It never actually touches the line. And if you can draw it through these points, make a secant through it, there comes a point where it eventually just goes off forever and doesn't actually touch anything. And that's a limit. It's a limiting factor. But that's a different kind of geometry. But it's close. It's on the right track. So this equation right here, we're going to put this up here and move it around, and we're going to take a good, nice look at it. And actually, I want to kind of blow it up so you can really just see it. I don't know how much bigger this is going to get. But G mu nu equals this statement here, R mu nu minus 1/2 R G mu nu. Now you see all these letters with this after it, the little Greek syllables, the Greek characters here. That means something, but it's not important to know what it means yet. We're not going to get there. We're not going to get there for a good little while. Remember, we still got 30 minutes to go to even, well, actually 20 minutes here in a 30-minute little mini-series kind of thing to even talk about what these physics do. Now, I want to go back and I want to pull up a comment from one of the forums here and explain to you why that matters. Okay, I scanned it for a second and I couldn't quite find out what I was looking for, but I found something that kind of gets after what I'm talking about here. We have this idea of manifolds, okay, topological manifolds. That's like you take some kind of flat thing and then you like make things happen to it, but you try to keep it that same shape, like basically bending and warping. The thing is, space can't tear, Like, it might be able to. Nobody really knows if that's a thing. There's any amount of energy that's relevant to the universe that can make that happen. And if it does happen, it probably bubbles off and creates whole new universes, because it has to be a huge amount of energy for space-time to just kind of come to a single point and then rip apart. And it's hard to think of it like bubbles anymore when you have to look at 4 dimensions. Remember, this is space and time this is happening to. That means like time rips in half, literally. You can think about space ripping in half. You can think about tearing a piece of paper, but what does time ripping in half mean? That's the hard bit here when you start thinking about these areas in space where you have a hole. You can have like a cup, like a ring that goes into space and kind of forms a wormhole. It's called an Einstein-Rosen bridge. It is a thing. It can happen. We just can't make it happen yet because it takes like I said, a huge amount of energy. And then these equations right here, these kind of give you a way to, hold on, let me scan these up a little bit. They're Maxwell's equations. If you know anything about physics, you've seen these guys before, right? That's pretty cool. Everybody likes those. So now we need to actually talk about what the hell these things are. So, like they said, when you have a black hole in space, it's going to affect the way things move around it, orbits. Copernicus and Kepler talked about orbits, and that was one of the first things on this list here if you were like kind of paying attention in the backward. Kepler and Copernicus on the revolutions of heavenly spheres, Kepler's laws of the rotations of heavenly bodies. These guys really had it all figured out. I've read these books, and I mean, Kepler, I think it was Kepler, I want to say it was Kepler, took the idea of music, like vibrations, and something going around something on a circle. Like you see my finger going first over here and then over here, and it doesn't really look much different than if I kind of do it this way. Because the same thing happens. You have that wave-like structure. So when you're orbiting around an object, it's going to take a path. It's really elliptical and just shoot out here for a while and go really slow around the sun. Or go really slow around here and then just shoot around the sun and finally it falls back into a well. It's like a penny. We've all seen these things at like science museums. Well, maybe not all of us. And if you haven't, I weep for your childhood. I seriously do. Because they're the coolest thing. You get, mommy, can I have a fucking penny? And I want to just throw it down the well. And you just watch it. If you get a good one. Only if you get a good one. Sometimes it just goes shrink, blink, and then just completely fail. But that's part of the fun is, mommy, can I have another penny? That one sucked. But then you do it as an adult, and then you know what it means, and you're like, gravity wells. And so you have different types of orbits and ways that things can fly around it. And so this becomes like a gravity well. Basically, they're like a whirlpool in space. This is just a computer diagram of like how space warps around it. And you can see this area of space right here should be like colored in down here, but it like flipped it up there because it was in that range. And then everything gets all turned up and upside down on itself and completely lensed around the other way. And that's what black holes do. They behave like these weird little coin sinks in space that just wobble and wobble all the way down. I'm not going to spend too much time here because there's not a lot of information on this page, but here's the thing you really need to look at. Newton's law of universal gravitation. Now, Newton had a few areas where he had no idea what he was talking about. God did it. And, if you've watched, like, Cosmos, you hear Neil deGrasse Tyson talk about this kind of thing all the time. He, insert God here. And that's basically what he did. But then Einstein figured out it's not a force. It's not spooky action at a distance. It's a gravity well, basically what it is. A large object in space will deform the trajectories that, Newton's first law particles would take. Or Newton's law of momentum, linear momentum, it's going to stay going in a straight line if it can, until it has a reason not to. But it's not only forces, it's divots. Like, I hope I make sense, because To anybody who has not heard this 1,000 times, you're just kind of like, what? How does that work? How do you do that to space? I mean, space-time is not static and immutable. It's a squishy ball of putty. Okay? You can grab yourself a piece of Play-Doh and then sit there and stretch it and morph it and try to make holes in it, poke holes in it in your finger. And you realize, like, when you try to poke a hole in it, you gotta really rip it apart to get it, because usually you can just make a dent in it. That's easy. You just kind of squish it and then it squishes in. But, like, you know, how much force would it take to push through your hand and, like, rip your hand open? Okay? That's the kind of different energies you can have. And in order to rip space and time, something really, really freaking big has to happen. I mean, like, an unimaginable amount of energy, okay? Like, that much energy. And then, like, you already can't imagine it. Now imagine, like, 400 times that. 4 billion trillion times that, all right? Like, think nuclear bomb and then multiply that by, like, I don't know, galaxies exploding like nuclear bombs. That's about how much it takes. It's a huge explosion. It's a huge amount of energy at once, and it just kind of like condenses on itself and sucks in on itself and becomes a black hole, and it warps. But it warps so severely that it just kind of goes, whee, everything just goes right around it and ends up on the other side. So that's like, normally you'll see lensing and then it'll be, a star will be a little bit off from where it should be in space, like that was a 1918 solar eclipse, stuff like that. Einstein saw Newton's stuff and went, dude, you're on the right track, but it's not just a force in the background. It's not just 2 point particles acting on each other. There's more to the story. It has to follow the trajectory in space-time that it is allowed to follow. So then you get these wonky tensor equations. These things, they don't really make sense. This tensor equals this group of tensors interplaying with each other, and you have to really start thinking about how it does that, and it becomes this giant chalkboard full of equations in order to get one solution for it, and that's just one of them. Like, you fill up a whole chalkboard, man. You know, you can think of like the university auditoriums with like 17 chalkboards in them. Yeah, they're all filled. They are all full up, and they're like, good, this is a solution to this equation. Everything checks out. That's one solution, and there are an infinite amount of solutions that can solve this function of how does mass squish space and time, and how does it squish distances between things, or, you know, stretch them, or squish the amount of time it takes to have events occur. Lots of questions have to be answered, but it takes like 17 chalkboards to get one of these solutions, and that's one of them I'm talking about today. So we're going to take a quick pause and, you know, let you read another excerpt from Alice in Wonderland. There was nothing so very remarkable in that, nor did Alice think it was so very much out of the way to hear the rabbit say to itself, oh dear, I shall be late." Then the rabbit actually took a watch out of its waistcoat pocket, looked at it, and then hurried on. Alice ran across the field after it, and fortunately was just in time to see it pop down a large rabbit hole under the hedge. We're going to take a break here for a second. So on down the rabbit hole we go. What is a tensor? We see all these T, mu, nu, H, G, everything tensors, okay? But we don't actually understand what they are. I mean, unless you have already gone through this rigmarole and you're just like, yeah, tensors, tell me something I don't know. Because at that point, you're like here on math, and people just doing physics are like, thinking I kind of get calculus. Okay, then you go to linear algebra and you say, I think I kind of get linear algebra. And I think I kind of get linear algebra. Me, I'm talking for myself. I think I kind of get linear algebra, so I can explain this thing to you, but I cannot solve it for the life of me. I'm not that good yet. But I can tell you exactly what it is and how I've come to understand them intuitively. And that's what really matters, is having the ability to kind of just look at this thing, do numerical transformations in your head and flip around and see what the numbers do. Okay, This is the stress energy momentum tensor. This is the most important tensor in the in that equation, is because that's the first one you're going to have to fill out. You're going to have to talk about what is this region's energy density? Like, what is the general scheme of it? If you go somewhere in space and in time, what changes? Like, what are the parameters? Okay, so these 0, 0. So this is time. All right. This is a time area, so this is just how much it's there. Like, it's time independent. I'm not saying all this quite correctly, but the energy density is basically just how much stuff there is. You don't need any amount of time to talk about how much stuff there is in space. It's energy density. You can think of energy as conflatable with mass. I say conflate because they're not equivalent. They are different ways of talking about the same thing, I think. That's what I've gotten so far from it. Yeah, momentum density. Momentum density is, space independent. This is how much something moves in these directions. So each of these little 0, 1, 0, 2, 0, 3, now you're talking about space. So how much, with respect to space and the x dimension, or with respect to time and the x dimension, and then the y dimension, and then the z dimension. Okay, so now you got yourself a little what is it? Right-hand rule. I'm left-handed, so I forget which one it actually is. But either way, you make yourself a grid line, and so you have it's pulling it this way for z, y, x, or however which way you want to orient your axes or point them, and you can do coordinate transformations on them. That's why you have the metric on the other side of the equation. It balances out and gives you a way to talk about where you are, like what value of 1, 2, 3 dimension, and then what value of time, and how they scale amongst each other, like where the next grid point is in relationship to the one behind it, or the one you're on. How to talk about taking steps in space. So these are tensors. I'm really running out of time here to explain the rest of this, but I don't know, I guess you guys are going to have to forgive like a 35-minute, I'm going to go overboard a bit, and if you're interested, you'll stay around, and if not, well, I mean, you're probably not here anyway. And if you are, I congratulate you, because I think I'm really kind of boring when I talk. But I do this just in hopes that, if it reaches 2 people, I call it a win, and they go, wow, I didn't think about it that way before. And I've had a lot of those moments happen to me, and I just want to kind of share some of them. So, okay, what's shear stress and pressure? Okay, that's all of your space components. That's like how, distances in space traversed when a force is applied. Like, it's time independent. You don't have to use time to talk about this. You don't have to use time to talk about shear stress, momentum, flux, and pressure, because they're things that just happen in space. Pressure happens in space. It's like a static thing. Like the pressure at one point in time, when you take away time and you take away how it flows through time and in what direction, let's say there's 3 dimensions of time, who knows? Maybe science comes up with a way to talk about that. And then you'd have to expand this out, so now you have more dimensions and more columns and rows here in this equation that they're all relevant, they're all related to each other. Shear stress is related to pressure, is related to momentum flux, momentum density, and energy density. They're all related. That's what this thing says. All right, moving on. I think we've jabbered about that one particular point enough. We have to actually figure out where it factors into the rest of the equation that we were looking at. Okay, so this is the other side of the equation. We're talking about metrics. Metrics are, you can also stack them up in a grid. And let me pull that up. I'm going to show you an example. This thing. So remember what we saw before? Remember all the RS? So now this looks different than the thing I showed before, because this RS here has been simplified, but you still have that over R. Remember that was there. So this inverse relationship here of this thing, it's still there. But what RS is it talks about this thing called the Schwarzchild radius, and that is, let's see, 2 mg over c squared. It's the distance at which this equals 0. RS equals 0 when R equals RS when R equals 0 or something like that. I can't remember how to say it. But give me a sec. I'm going to go back to this. You go back all the way to, where was it? Here on this page. I covered it up, but then you have this thing. Remember this? This 2m over r, 1 and 2m over r, and then this rs over r. And that's really what it comes. It takes these guys out of here away from their differentials and kind of stacks them up in a neat little way like this. So then you have the sphere functions over here. This is, by the way, in kind of like spherical coordinates, but it's a completely different thing. So it operates on the values of this, what was it? All 4 of these coordinates, they do matrix multiplication on each other with each of the values here, which talk about your energy density on all these things, okay? So they have to equal each other with some constants and stuff, so that's what the rest of that equation, that jumbled mess, looks like. Oh yeah, I already had it here. So Minkowski spacetime has this form here, and this all zeros where there's blank here, but it's a matrix that looks like this, and it's denoted d or eta mu nu. That's your, it's flat spacetime. It's space-time with like unit mass and just basically the simple, simple-minded space where nothing important is happening at all. But then we talk about, then we multiply this matrix here by some other function and end up with, this is your answer. Well, what is that other function? It's that stress energy momentum tensor. So you end up with this R equals 2 mg over c squared. I said that earlier. And it also has this neat little thing where the photon sphere, that's the outside rim of everything you can see. This is where photons have a stable, not in-falling radius. That means they just stay going around in a circle around the black hole forever. Once they get locked there, they're never going to leave. That's another little interesting thing about black holes, is it just kind of locks things in space and then it kind of flips it around on itself. But so in order to actually talk about how to take a step into a black hole, you have to understand how to take a step on the shape of surface that this thing describes. Now you cannot actually visualize that in your head because remember, we're going through space and time. Up here we got space on this axis right here, this row. This column here will go out to a vector and make one, okay, so let's move this over here. So we're going to make this blue space right here, we're going to call this another vector. So everything in this column here is going to multiply out by the first thing in that vector, and you're going to have some vector at one point in space where it's going. It's just going that way. That's how to take a step. So then you multiply it by this thing, and then soon here you're going to get a vector that tells you where you're oriented, which way you're going in space and time. And you're always going to be going forward in time, but somewhere in space. And it'll orient you, and then it'll keep doing that continuously, and then you can actually make up a map of it. Especially if you remove, like, say, time from it, and you just get this static time invariant mesh of, like, taking individual quantized steps. You kind of build a mesh of it, and that's why they give you that little funnel-looking thing that kind of looks like a black hole. And so, you guys can read. I don't need to read this all to you. But let me kind of go over it. We have a framework. We use a bunch of tactics and create a density with a strong gravitational field that light no longer escapes. That's a black hole. Okay. And Then it forms a gravity well, and it falls inward radially towards the center. Okay, approaching the black hole. That's the important one. This guy right here. For bodies approaching the black hole, I'll read one of them to you because this is important. Time dilates and lengths contract in correspondence with the physics of special relativity. What? You've never heard anything about physics before. We're gonna put yourself into a very brand new mind. Why can't I even say that out loud and it sounds like it means something? Well, we're almost there. That's really kind of a story for another day. That's special relativity. What I've just described is general relativity. I'm talking about how we talk about curved surfaces in space and time. And now, since I'm kind of going over my time, it's about time I got to where we're talking about some black hole stuff. And this is your reward for sitting with me all this time. I'm going to tell you what black holes do. Right after this little message here, we're going to take a break and we're going to have some sponsors talk to you for a second. Okay, so your reward for seeing that ad for a little while is you get to hear me actually explain what we've come up with about black holes. What statements are we able to make pretty much unequivocally about them? Time near black hole behaves quite differently than we're used to. Okay, we can say that. That can mean whatever we want it to, but at the end of the day, that's true. Time near black holes behaves very differently. Clocks start tick tock, tick tock, tick tock, tick tock, and light blue shits. That's like, well, at first, you kind of go in there, and let's say you're in the black hole. You're watching like all of space and time kind of come together in this blinding flash of light. It all just kind of like there's a little thing on YouTube where you can actually just kind of see falling into a black hole in a VR goggles, and you kind of look around in real time. And I don't know how they came up with it, but like knowing the equations and everything, they've nailed it, man. I'll find the link for you and put it in the description. But yeah, that's a reward just by itself to be shown that gem. It starts to describe an event horizon where all of our understanding of space and time is essentially paradoxical at best and downright lunacy at worst. Everything I've just said, if you have a brand new physics mind and you're just kind of looking into getting into stars and black holes and what are black holes and dark matter, what are all the mysteries in physics, well, what mystery do I feel like I have the guts to chase down? Now, this is one of them I've been working at for a while. And I mean, I'm no Leonard Susskind. I can't fill a chalkboard with equations and just kind of like solve them in front of you, but I can talk about the same things he does and give you a little bit of intuition. And a little bit of, I don't know, I want to say a way to think about it, something to think about. You have this squishy ball of silly putty that is space and time all as one unit. And you can pull it apart. So like if you're you could do really cool things with it and think about how long it would take for an ant to walk past it. Now you can like bamboozle an ant walking on it by like pulling the silly putty apart, and then the ant has to walk even longer to get back over the end of the bridge. Stuff like that is like real talk physics. Okay, that's the cool thing about physics, is that you start learning things like this, and then you get this big cheesy grin on your face like I do when you're talking about it, because you get it. It makes sense. And time and space just kind of stretch, and they warp, and they squish, and they squash, and you can talk about all kinds of different shapes that they can make. And in the abstract space where things don't actually have anything we know like shape, like what is the shape of my hand? I can see my hand, I can trace its shape in front of me. Well, you can't do that with lines in space-time, because you'd have to go into another dimension. You'd have to meet reality at right angles, to quote Douglas Adams. the universe as it is right now is just kind of like a shadow of the fourth dimension of time. It's one tick of the clock, one moment, one exact point in space and time, one infinitesimal quanta of time. Planck's epic. That thing, what is that? How do you talk about that? How do you start finally getting it down to a continuum where you can start talking about one, like a bubble of time moving and kind of getting a little bit farther away from another bubble in time? So it takes something going across that field to walk farther to the next moment. What does that mean? That's what you have to think about when you get into general relativity, because simply put, if you can never watch something fall into the event horizon, how can you get experimental observations that help confirm the theory the math throws at us? I mean, like, if the math is wrong, how does it affect the theory? Okay, well, I mean, we can ask these questions and we can talk about this philosophically, but the math is not wrong, it's approximate. We know that's what it does, we just don't know to what extent and why and how it does it. We're not clear on the details. We just see it, and that's one of the solutions. It's a solution of an equation that governs how matter and this continuum idea, this silly putty idea of space and time interact. So how does a force push the silly putty? So you can think about that. You drop a bowling ball into the silly putty and you squish it around the bowling ball, and now you can just kind of like pull the bowling ball out and watch a coin roll around it. And even the mass of the coin starts kind of warping the little, thin membrane of the silly putty that it was warped into. I mean, that's a real kind of way of talking about how things behave in space. And how does it affect our understanding of the space-time continuum if we don't have the right math? Well, who knows? I mean, we can think about that, and that's why it's important to write more equations, more solutions down on a chalkboard and go, okay, that one makes sense. So if you squish it this way, then it moves like this, and now we don't have any lumps or tears. Because like, but what if we do have a tear? And then the other scientists in the room would just look at him like, did you have to? Did you just have to bring it up? Did you? Because then they're all going to be like, no, it can't tear. You can't have enough energy. Well, sure it can tear, man. You just have to have enough energy. And then everybody, it's chaos. Okay, that would be like the break room in the General Relativity staff lounge at the university. I mean, that's just like that's how much of a divide it creates in the community, man. It's wild math, and it tells us weird things about the world. So for the last little bit of this, we're going to just kind of play around and look at some slides, because this was a thing I did for college, and it wasn't very fun. But we're going to fill up this and make another 45 minutes. So if you followed me for 15 minutes, you get some ads thrown in your face. You follow me through 30, you get some more ads thrown in your face. I make a couple more pennies, and you get some very, very valuable knowledge. And you just keep going farther and farther down the rabbit hole with me, which is the whole point of drunk physics, right? That's why now I kind of wish I had a gin and tonic to sit here and get classy with it. Talk about space and time like a Brits would. Because where did it come from? Where did we get all this stuff? We got it from Newton. We got it from, I want to say Kepler was English. I'm not sure where Kepler was from. It came from all over the place. That's why they say it's just a theory. It's just a theory. It's a wild-ass guess. No, it's not actually, because, you get that staff room at the lounge, but then you get them all at a conference, and then they're all just squabbling over, well, if you just flip the sign this way, then look what happens. Then it blows up in your face, and that's not cool, but, that has to be a thing you need to be able to do. Oh, yeah, I added this little thing. I'm really stressed out about this whole black hole thing, yeah, because it's funny, because if you're a physicist, you just kind of, stress on space-time, yeah, I get it. It's stress, energy, momentum, blah, blah, blah. Energy is equivalent to the speed of light squared times the mass of the object. That one guy who told you about physics that one time. Yeah, who was that? Now, if you can tell me who that is, you're already you're already farther enough down the rabbit hole. And another moment down went Alice after it, never once considering how in the world she was to get out again. The rabbit hole went straight on like a tunnel for some way, and then dipped suddenly down. So suddenly that Alice had not a moment to think about slipping or stopping herself before she found herself falling down a very deep well. More Alice in Wonderland. I was really high when I wrote this or something, man. I don't know, because this is just getting out there. Ideas without numbers. Philosophy is a dangerous place to tread where facts and physics are concerned. I mean, we just kind of started thinking about that exact idea. Causality and sequences of events and determine our understanding of physics. Okay, I'm starting to have been talking too long and not reading. My brain's not working so well with it. So, I mean, we get this different idea of causality. This understanding is distorted by mathematics, but we can still make some sense of it. Yeah, I mean, fair enough statement. We can. Now we have to talk about, what about these special cases of causality, where it's not like everyday thing. It's, you know, it's particle physics, where particles just start acting freaking bizarre in general. What does that mean for us as people who are also made of these particles? You know, what does time look like when it's slower? How do you, like, what would that experience be like watching somebody do it? And I think about like going into a black hole a lot, and like, or going near it and watching some other poor unfortunate thing get thrown into it that's sentient but somehow manages to survive it. So it's not, you know, cruelty-free thought experiments. You know, it's this sentient blob of energy that goes over there and goes through it and reports back when somehow it manages to find me again and tells me what it was like. I mean, that's kind of what the math is for me. It's that sentient blob of energy that can go down the black hole for me so I don't have to. Time between events approaches infinity to the outside observer when an observable object reaches the event horizon of a black hole. The point of no return is thought of as the event horizon. A singularity is a place where space-time, energy, thermodynamics, quantum mechanics, basically every intuition you have about everything is just blown to shit. You can't make sense of anything when you get to the point that you know you hit the center of that black hole. There's no way to describe what that means. And so, dude, like, what if so you have to talk about that in terms of inertial reference frames. So two things are moving next to each other. They're going around it. We're spinning around and around and around this circle. And this is where it starts moving a little faster, because then it's just statements. I don't have to explain myself. We already kind of got an idea. But like I said before, you know, so are black holes like paper shredders, CD burners, or what? Well, you go down, you reach the event horizon, you're stuck in something like time and space, all the information about Ted smeared all over an accretion disk. Like, basically like you just wrote Bill onto the surface, and Ted just goes, "Bill, man, I can like see your whole face. It's like smushed and warped." I mean, so what does it shred the energy? Does it shred Bill up? No, I think it just kind of smears him out, and all of his quantum information is just wrote there forever in space, just stuck. Like, I mean, obviously he's going to get shredded by the forces, but his information is going to be there. Or is it? That's a big question. Don't get physicists started on that question. I got 1 minute left. I mean, we're going to let you imagine what that's like. Time dilates, it all gets wonky and warpy, and seriously, this has been 45 minutes of a really good time, but our time is up. So if you like what you hear, buy me a beer. Follow me on Patreon. I will post, and, you know, hell, Derelict on Facebook. that's how you got here, probably, the first of you. So please subscribe, and the link's down below. Everybody says that. Why do they say that? Well, it makes me money, man. Why do you think I make you watch these videos? I do this shit for free. And it's not fun to, like, just sit there and go, when is the ad revenue going to start coming? You know, I got to wait for 150 fucking views. And, you know, I don't want to just do this and just feel like I'm wasting my time. So give me some love, man. You know? All of you, take care. Stay away from sharp objects and black holes. This has been Drunk Physics. Except I wasn't drunk. Take care.